Good day, everyone. My name is Kirubagara, and this presentation is titled Engineering Analysis of Pressure Drops in Packed Columns. The main question is how gas liquid contact be improved without creating excessive flow resistance and energy consumption. This study evaluates the effects of gas velocity and liquid loading on pressure drop, blower energy, and packed column design. So, what is happening inside the packed column? Inside the column, liquid flows downward while gas moves upwards through 16 millimeter Paul rings. This arrangement is known as countercurrent flow. The packing provides larger wetted surface, allowing the effective gas-liquid contact for mass transfer. However, it also forces the gas through narrow and irregular spaces. It is similar to moving through a crowded hallway. Movement is possible, but resistance is created. Therefore, the same packing that supports mass transfer also creates hydraulic resistance and pressure loss. Why pressure drop increases? In the dry bed, most of the void spaces are available for gas flow, giving a calculated pressure drop of 13.18 Pascal. When liquid is introduced, liquid films and hold up occupy part of this space. The gas pathway becomes narrower and pressure drop increases to 105.15 Pascal. Simply, less available space creates greater resistance and a higher pressure drop. The engineering model, the Ergun equation was used as a screening model. It separates pressure drop into viscous and inertial resistance. Viscous resistance increases approximately linearly with gas velocity, while inertial resistance depends on velocity square. This explains why pressure drop increases rapidly at higher gas velocities. For wet operation, liquid holdup was used to reduce the effective gas voidage, showing how liquid restrict the available gas flow area. However, this remains a screening estimate rather than a final design guarantee. For the base case and model check, the wet pressure drop was almost 8 times higher than the dry bed value. To check the result, a second liquid holder model was applied. It predicted 117.43 Pascal which was 11.7% higher than the original estimate. Changing the predicted holdup by plus or minus 10% produced a pressure drop range of 91.22 to 120.43 Pascal. This is not a statistical confidence interval, it is a model input sensitivity range. The difference shows that the trend is useful, but the exact wet pressure drop requires experimental or manufacturer validation. Effects of operating variables. As liquid loading increased, pressure drop rose from 58.22 to 166.37 Pascal because more liquid reduced the gas void space. When a gas velocity increased from zero point 0.1 to zero point 0.3 meters per second, pressure drop increased from 24.28 to 117.09 Pascal. Electricity consumption also increased approximately 14.5 times. This shows that gas velocity is a major driver for both pressure drop and energy demand. And the design is a trade-off. At fixed throughput, lowering gas velocity reduces electricity consumption and indirect emission by 57.8%. However, the required column diameter increased by 22.5%, while packing volume increased by 50%. So, in engineering, there's usually no free lunch. A larger column requires more construction material, more packing, and potentially a more carefully designed liquid distributor. Therefore, the lowest pressure drop is not automatically the best design. Energy saving must be balanced against equipment size, material use, mass transfer performance, and flooding safety. As a conclusion and a recommendation, pressure drop connects column hydraulic with energy consumption, mass transfer, and process safety. Wet operation greatly increase resistance, while higher gas velocity and liquid loading increase pressure drop. The recommended approach is to select a balanced operating point, supported by wet pressure drop data, flooding checks, and HTU and NTU analysis. The goal is not simply minimum pressure drop, it is safe, efficient, and effective separation. Thank you for listening.